Okay, somehow battery died. So come again, back again. Archimedes' principle, I was saying that means or is that that any solid, totally or partially submerged into a fluid experiences an upward buoyancy force equal in magnitude to the weight of displaced fluid. That's the key point. Weight of displaced fluid. This is the demo number 3. The demo show you. Let's give you demo number 2, but because it needs a rotatory chair, T3. Okay, and I had to bring it in, and I couldn't bring it home. I might record it in my office. Okay, weight of displaced fluid. Why is this a principle? Because Archimedes, or for some centuries, it worked like that. Weight of displaced fluid was that force called mf, the mass of displaced fluid, and so the weight of displaced fluid is a weight is a force of m times gravity. Yeah, so why? Okay, the idea is you can understand this principle using action-reaction, the third law of Newton. So for the solid to enter into the fluid, it has to push away a quantity of fluid. How much? How much? Just to fit in. The volume of the solid is pushed away. So the solid pushes the liquid in that direction. So as a reaction, the liquid pushes back the solid in the and this is this buoyancy force. Okay, can we work with it more? Yes, this is the buoyancy force, right? Call it BF, buoyancy force. Can we work a little more with it? Yes, we can. We can apply, for instance, the definition that we saw about density. Density of displaced fluid. Density is mass of displaced fluid divided by the volume of the fluid. So if I just solve this equation for MF, MF is going to be the density of displaced fluid times the volume of displaced fluid. So I can substitute there, rho F, I put the G in the middle because I like it that way, but I just put it this, MF, when it says MF, I put rho F VF, okay? Yeah, what is VF? What is the volume of displaced fluid? So this, you have an intuition about Archimedes' principle, because tell me who hasn't soaked a cookie or a cake or a madeleine or a croissant into coffee or milk. So I discovered this when I was young, that I love this. I think I explained this to you. Okay, then when I put it inside, the milk level rise. So how to be careful. In other words, how could you calculate the volume of a cow? A volume of the cows are not spherical, and not simple or cubic. Even in maybe in Minecraft, but not in the real world. So it's complicated. Let's discover how to do it. Putting the cow inside a fluid is the best way. Okay, so this is the level of the fluid. And this is the cow. Let me do it in a very simple way. Okay, this is the cow. So if I put the cow into a big container full of a big tank full of water, what will happen? The water level will rise, okay? This is our cow, so we don't want the cow to die, so let's give it a scuba dive. Scuba or scuba tube, or I don't remember. So you can read. So it was discovered that this volume of displaced fluid, the volume that the cow has to push away to enter the fluid, is exactly the volume of the solid, or in other words, the volume of the cow. The volume of displaced fluid. This is displaced fluid is the volume of the solid. Why? Because the solid displaces the fluid. Volume of the solid. V is volume all the time. So, where I was here. Here I can go back and substitute. First I substitute there, the MF here, okay, and now I substitute there. The what rho F G V F, since VF equal VS, F equal VS, so that's, yes, this is the volume of the solid inside the liquid, okay, because it's inside. This is the volume of the solid inside. So in this case, the buoyancy force is going to be the equation that can be used to make calculation, estimation, and stuff is this. The buoyancy force that pushes the solid outwards is the density of the fluid times the gravity times volume of the solid underwater. Okay, must be underwater because that's our requirement. Underwater, solid underwater. What can we apply this equation for? I think we have enough time to foresee, to anticipate the behavior of a solid. If it's going to see, we tend to think that, I don't know, the solids that are heavy, they're very heavy, sink. But this quality, heavy weight, is not what is responsible of buoyancy, because we have like big ships made out of steel, okay, they don't sink. So let's analyze buoyancy. Okay, buoyancy in 3 cases. The first case is when the solid is inside, okay, and it's not moving, it's not going upwards or downwards. So to achieve this, the solid not moving, because we have the force, right? We have the weight. Mg is the weight of the solid. We put it ms, the mass of the solid, times gravity is the weight, and we have the buoyancy force. So if the first case the solid is still not moving, still solid, what happens? So we have forces. We have a force, upward force, and we have a downward force. But the solid is still. The only explanation is that the forces are the same. Even though the forces are being applied, they're equal, so they don't cancel. So